This week we're going to be covering speed, velocity, different types of energy, and how those energies transfer from one form to another. So we're going to start with Objective 67. I can describe speed and velocity and calculate speed and velocity. So speed is a measure of the distance covered over a period of time. So how fast you're going. Okay? The amount of distance you cover in a certain amount of time. Velocity, the only difference with velocity is that velocity also has a specific direction. So velocity is the measure of a distance you cover in a specific direction over a period of time. So if you look down here, our formulas are exactly the same except velocity you add a direction with. Okay? So a lot of people use speed and velocity interchangeably. That's because they're calculated the same way. When I ask you a speed, you would say something like 50 miles per hour or 65 miles per hour. If I ask you for a velocity, you're going to say 50 miles per hour heading east, or 50 miles per hour heading west, or north or south. You could even use things like 50 miles per hour to the left or to the right. All of those work as long as you are including a direction with your speed, then it becomes a velocity. Okay, so if you look over here at this, it says speed is simply how fast you're traveling. Velocity is speed in a direction. Okay? Alright, moving on. Distance time graphs versus speed time graphs. And we've talked about distance time graphs already. You guys are already familiar with those because we worked on those with our graphing unit. Okay, so we are going to fill these in on your notes. So if we look at this first line right here, we see it's a straight line, and because the slope is steep, we know that it's going a fast, steady speed, because as time increases, your distance is increasing the same amount, so you have that flat line indicating that it's a fast, steady speed. Okay, again, this line here is going to indicate a steady speed too. It's just not as fast because your slope is less. Okay, and then we have a flat line. Remember, our flat lines are going to indicate that our object is not moving, or that it is stationary. Okay, your distance is staying the exact same. As time moves on, your distance is not changing, so that object is staying still. Remember, we talked about in our graphing stories that Johnny's mom goes to the store and then she's at the store for 2 hours. Okay, this is the 2 hours. She stayed in one spot for 2 hours. I'm going to erase some of this out of the way so we can look at some of the other ones. Okay, and because this is a distance time graph, because we are going down here, remember our distance is decreasing. We're returning to where we started from. Okay, it's showing a steady speed again because it is a flat line. You don't have any curves in your line, but that our distance is decreasing. Okay. All right, and remember when we have our curve in our line, that is going to indicate acceleration or deceleration. In this case, it's going to be acceleration because it is curved upwards like this, and if it was getting slower, it would look like that. Okay, so make sure you get those written down in your notes, and then we're going to talk about speed time graphs. Now, we have similar shapes here, okay, but we have different things happening. In a speed time graph, you guys need to pay attention to whether it says distance time or speed time. So this means we're speeding up. This means we're going the same speed. So for this entire time while we are flat here, that means we are going the same exact speed. Remember, in a distance time graph, that flat line indicates that you're not moving at all. This one indicates that you're staying the same speed. Then we're going to accelerate again, where our speed is going up as time increases. And then this line right here is going to indicate that we are slowing down, steady deceleration. Remember, this line means that we're returning to the start. Our distance is decreasing. But because this is a speed time graph, this is going to indicate that you are slowing down. I'm going to erase this so that you can label those on your video notes. Okay? When you guys are looking at these graphs and you're trying to determine what's going on, please, please, please make sure you are looking at your X and Y axis to determine what is happening. Alright, let's move on. Objective 66. I can describe the law of conservation of energy. You guys learned about the law of conservation of mass last year, which says mass cannot be created or destroyed. All the mass that's in the universe is already here, and it can change forms. Same thing with energy. The law of conservation of energy says that energy can neither be created nor destroyed. Energy changes from one form to another. The total energy of an object never changes. So energy can change from one form to another, but we can't destroy energy and we can't create energy. All that is available is already here. It just changes from one form to another. Objective 68, I can describe the different types of energy. We're going to start with potential and kinetic energy, and you guys have a little bit of background in that because you have already seen that in your Newton's Laws word search. It asked you for another word for potential energy, and if a skier is going downhill, what kind of energy does he have? And that would be kinetic energy. So we'll first start with potential energy. Potential energy is stored energy. It's energy that is available but is not being used. Okay, so we usually say that potential energy is energy, not the eraser, let's try the marker, energy at rest. Okay, it is not being used. Okay, next is kinetic energy. Then kinetic energy is energy in motion. Okay, so that skier going down a hill, he has kinetic energy. Okay, kinetic energy is the energy an object has because of its motion, and kinetic energy depends on the mass and velocity of an object, and we're going to talk about that in just a second when we get to look at the roller coaster. If you look over here, this ball that's being held has potential energy because it's not in motion, it's at rest. But because it's being held up in the air, it's called gravitational potential energy, and we'll get more specific here when we do some labs in class. And then in this example, the ball is dropped, which means it's moving, so now it has kinetic energy because the ball is in motion. Mechanical energy. The best way to identify something if it has mechanical energy is to determine if it has moving parts or not. Okay, mechanical energy is the energy an object has because of its motion or position. It's the total amount of kinetic and potential energy in a system. Okay, so examples of things that have mechanical energy, again, you're looking for moving parts. That is the key to mechanical energy. If it has moving, if it has moving parts, okay, then it's mechanical. So wind-up toys, a pogo stick, wind power uses mechanical energy because it makes the windmill itself rotate around. Okay, so moving parts is going to give you mechanical energy. Another type of energy is electrical energy. I know you guys are all familiar with that. It's energy caused by the movement of electrons. And I know you learned about electrons last year in 6th grade. Remember, your atoms are made up of protons, neutrons, and electrons. So electrical energy is the movement of those electrons. Okay? They're easily transported through power lines and can be converted to other forms of energy. You guys know that because we use that all the time. You plug in your cell phone to make it charge. We use that electrical energy to fill up our battery, which is a form of chemical energy, which we're getting to next. All right, chemical energy, energy that's available for release from chemical reactions. If you have to identify something as chemical energy, you are looking for anything that uses batteries or is in food, okay? Because our body breaks down food into chemical energy for us to use, for our muscles to use, and for the chemical reactions in the food allows us to have energy in our bodies to use, to move, to talk, to sing, whatever we're doing. That energy is chemical energy, and that comes from the food we eat. Okay, so anytime there's a chemical reaction or anytime anything uses a battery, so we're just talking about our cell phones, right? We use electrical energy to plug in our phones and charge that battery. That battery uses chemical energy and transfers it to electrical energy so we can use it. And I know this is sounding a little bit complicated as I'm talking about how energy changes from one form to another, but I promise by the time we're done with it, you will understand it. All right, the next type of energy is nuclear energy. Energy that is stored in the nucleus of an atom. So remember, last year, you have protons, which are positive, and you have neutrons, which are neutral. They're neither positive nor negative. Okay? And then out here in the outer rings, you have electrons, and they're negatively charged. So inside the nucleus, you have this tightly packed center of protons and neutrons. And nuclear energy breaks apart this nucleus. And when the nucleus is broken apart, a huge amount of energy is released. And that energy is used in nuclear power plants, which are used to give us electrical energy. Okay, if any of you have been out to Holly Springs, the Harris electrical power plant is out there, and they provide energy for surrounding areas. Okay, a power plant can provide energy for, I think, up to 750,000 homes and businesses in an area. Okay, so about 750,000 people are getting energy from one power plant. Okay, and that could be more or less depending on the electrical needs of what's around the power plant, but that's just a good guesstimate of how much energy one nuclear power plant provides. So we're looking, nuclear energy is from the nucleus of an atom. When the bond between protons and neutrons is broken apart, then a huge amount of nuclear energy is released. Green energy. This isn't a specific type of energy, but it covers the types of energy that are available that do not pollute the earth. Okay? There is actually in North Carolina a law that says that a certain amount of the electrical needs in North Carolina need to come from green energy sources. And I think it's about 3%. And that percentage is going to grow as the years go on. I think by the year 2020, we have to be at close to 11% of our electrical needs need to come from green energy. So if you look at this picture, you can see a couple different things where we get green energy from. Okay, so wind turbines is one. We don't have a lot of those in North Carolina. There's been a law that's been passed that they can't go in certain places because people don't like the aesthetic look, and they want to preserve the mountainous views in North Carolina. Other places don't have them because there's not a lot of wind, so they wouldn't be a good source of energy because there's not a lot of wind there. Other types of green energy is solar power, and you see those all over the place. You guys know I'm a Redskins fan. If you've ever been to FedEx Field, the FedEx Field is powered by solar panels. They have solar panels all over the place in the stadium, and also in the parking lot. There's solar panels that are set up in the parking lot to help provide and offset energy costs. And last, you can see there's like trees and stuff back here. Those are called biomass. That's biomass energy that we get from burning things like trees or coal or things like that. That's called biomass. Okay. Other types of energy that are available that we are just going to cover quick because you've already covered them previously. Heat energy, also known as thermal energy. Light energy is radiant energy, and of course sound energy, and you covered that in 6th grade. I think you guys covered light and sound in 6th grade, so we're not going to spend a lot of time on it. Okay, and that gives us, brings us to Objective 69, where it says, I can describe how energy changes from one form to another. I was talking to you about this a little bit, but let's go a little bit more in depth. So remember, the law of conservation of energy says that energy cannot be created or destroyed. All the energy that we already have is here. It changes from one form to another. So if we look at our first example, this ice cream, because it's food, remember anything that's food or battery related is chemical energy. And that food gives us energy to ride a bike. And because it's moving parts, our legs are moving, our joints are moving, and the parts of the bike are moving, that is mechanical energy. Okay, so that is going to be a transfer from chemical to mechanical. Okay, in our next example, we have the sun, which is radiant energy. Okay, that's light energy. And we know that through photosynthesis, our plants change our light energy into chemical energy, which is food, right? Photosynthesis provides food for plants, so radiant to chemical. In our next one, this is gasoline. Okay, that's chemical. That's going to be a stored type of energy, and it's stored in chemical form. and we put it in our car, and then our car uses the engine to use that chemical gasoline, that energy, and changes it into mechanical energy. Remember, moving parts so that our motor runs and our wheels turn and we can move our car. So that's a chemical to mechanical example. And then last, we have electrical to thermal. So anything that you have to plug in, guys, that is starting with electricity. And this is a stove over here, and we know that we use thermal energy or heat energy to cook our food. Okay, so those are a few examples of how energy changes from one form to another in everyday situations that we are familiar with. Okay? All right, moving on. Here's a really great example. I'm just going to talk to you as this is moving because once I start writing, it will stop going up and down. But pay attention as the roller coaster goes up on the top, look at how much potential energy you have. So it's about to start over, so look at the potential energy as it's going up the hill. Potential energy is the highest, and at the bottom, kinetic energy is the highest. So you can see how we're changing from stored energy to energy in motion. So I'm going to pause this real quick and go into writing mode so I can just point a couple things out. So here, if I can get my marker, so right here and right here and right here. When we are at the highest points on our roller coaster, our potential energy is going to be the greatest. As our roller coaster is moving downward to the lowest points, okay, that's when our kinetic energy is going to be the greatest. And during the changeover from potential to kinetic, right here, our potential is going down and kinetic is going up. Okay, I'm going to get out of drawing mode so that you can take a look at it one more time as it's going through. Alright, so here we're going up, up, up. Potential energy goes up, and as we start to go down, it's going to switch. Kinetic energy is high. And you can see how it is changing from one form. The amount of energy never changed. The potential and kinetic energy, it was just transferred from one to another, but the total amount of energy available didn't change. Okay? Again, a reminder that energy cannot be created or destroyed. I told you that's the law of conservation of energy, and that energy changes forms. All the energy available is already here on Earth. Some other examples, we talked about eating with the ice cream. Eating gives our body chemical energy, and our bodies change that food into mechanical energy when we move our body. Another example is charging our cell phones. We start with electrical energy because we plug that into the wall, and it changes it into the form of chemical energy that is stored in the form of the battery. And then once we unplug our phone and we're using that battery, we're using another energy transfer, which is going from chemical, from the battery, to electrical, and probably some radiant because the light on your phone is going to come on. Okay, so that backlight comes on. You're on your phone, you're typing things, that's using electrical energy and also light energy. And probably some thermal energy too, because you know if you're on your cell phone too long, it starts to heat up. Okay, so that chemical energy is transferring to all those different types of energies. Okay, and I think that might be it for this week. Yep, if you have any questions, make sure you ask them. We'll be doing lots of labs about energy transformation this week. All right, have a great night. Bye.